In a previous video, you have learned how you can determine whether a planar simple closed curve has a positive or a negative orientation. In this video, you will learn how an orientation of an orientable bounded surface induces an orientation of the boundary curve of this surface, which we call the positive orientation of the boundary curve of the surface. Let us start with repeating what we learned about the positive orientation of a planar simple closed curve. A simple closed curve C has a positive orientation if the enclosed region D is always on the left as you traverse along the curve C. For a planar simple closed curve, we can visualize this with small arrows. In this video, we want to derive the orientation of a boundary curve of a surface from the orientation of that surface. For this, we need to go away from the plane and move to the three-dimensional space. The plane can be seen as a subspace of three-dimensional space, so let us view our curve in three-dimensional space. As you can see, our planar curve C has now become a space curve, and the plane region D has become a surface, which we will call S. Some people consider the normal vector 0, 0, 1 as the natural orientation of the xy plane, and similar for the surface S. Note that you obtain this orientation if you consider the surface S as the graph of the equation z is equal to 0. But now we see that the positive orientation of the space curve C is induced by the orientation of the surface S by the following rule. If you visualize yourself as walking on this curve in space, you can see that your body, from toe to head, always points in the same direction as the normal vector of the surface S, and the surface S is always to your left. We can generalize this observation to general orientable surfaces with some boundary curve in the following way. Assume S is a bounded orientable surface with a simple closed boundary curve C. Assume S has an orientation with unit normal vector n. The orientation of C is positive if walking along the curve C with your body pointing in the direction of the normal n keeps the surface S always to your left. Note that if you change the orientation of the surface, also the induced orientation of the curve can change. This definition we can use for a variety of bounded oriented surfaces and their boundary curves. For example, consider this surface S. In this case, the surface S is easily described by this equation and these bounds. We can choose the orientation of the surface S ourselves, or by the use of a parametrization of S. I have chosen to use the standard formulas for a graph to obtain the upward unit normal vectors of the surface S, and here you can see a few of them orthogonal to the surface. The boundary curve C of this surface is depicted with this green line, which, as you can see, is a simple closed space curve. If you think of yourself as standing on the curve C with your body from toe to head, pointing in the direction of the normal vectors, and stretch your left arm out, you can see that the surface S is in this case always to the left of you if you stand like shown here. So we must conclude that if we want to have the space curve to have a positive orientation, we must choose a parametrization for C, which gives these arrows as the orientation. Note that another parametrization of the surface may give another set of normal vectors, which will cause a different orientation of the boundary curve. For our surface, a different parametrization could lead to the downward unit normal vectors instead of the upward unit normal vectors. So let us do the same analysis with the downward unit normal vectors. Again, we have the same surface S, but now we take this choice for the normal vectors of the surface. Because the normal vectors now point downward, this should be the orientation of the space curve to make the orientation positive. Note that if you draw yourself on the curve again, you should be upside down. This is not a problem, because in reality you will not walk along such space curves. Well, you now know how to find the positive orientation for a simple closed boundary curve of a bounded oriented surface. You can use these concepts of orientation in a theorem called Stokes' theorem, which is a more general version of Green's theorem. But that is for another time.